telling me things like this. My name is Matt Langford. I'm a research fellow here at the MSI, a couple of floors up. My research area is typically referred to as geometric analysis, and that's a research area which is at the interface between partial differential equations and differential geometry. So PDE, partial differential equations, that's the analysis part. And on the other side you have geometry, namely differential geometry. And so geometric analysis involves the use of analytic tools to study geometric objects. Okay, so, and this talk is about the deformation of geometric objects according to certain kinds of partial differential equations. So this is very much in the vein of studying geometric objects using partial differential equations. So hopefully I just want to, hopefully you get something out of this talk. I just want to give a very qualitative introduction to this field and show you how useful and beautiful it can be. Okay, so let's begin with the classical setting, and that is of the classical heat equation. So recall that the heat equation of Fourier, introduced by Fourier for modeling of the temperature of an object, also known as the diffusion equation, is the equation ddt of a function u is equated to its Laplacian. Okay, so remember the Laplacian is just the sum of the pure sums. So in two variables, x and y, it's just uxx plus uyy. And here u is going to be some function that goes, it's defined on some, say, open set in space and some open set of time. So that's a subset of space, which we can take to be n-dimensional because we're mature enough to deal with n dimensions. But of course we always just think in 1, 2, or 3. But we have some function u depending on some number of spatial variables and one time variable, and the time derivative is equated to its Laplacian. So this equation, which hopefully you will have seen before, it's one of the first partial differential equations you see, along with the wave equation and Laplace equation. But the heat equation, it displays some remarkable properties. So it displays remarkable properties. Okay, so I mean, let's forget about heat for a second. Let's talk about the remarkable analytical properties that this equation displays. So the first very important one is well-posedness, which when you think about it is a pretty remarkable property. It tells us that whenever we specify some initial and boundary conditions, so given suitable initial boundary conditions. So on the parabolic cylinder, so we restrict u to say t equals 0, or restricted to, I'll say, conditions on t equals 0 and the boundary of omega. So if we specify suitable conditions at some initial time and on the boundary, the spatial boundary, then we always get a solution. So we can always start off this heat flow. So if you have some initial temperature configuration, the future configuration can be determined by this equation. And moreover, it will be uniquely determined. So there's exactly one future evolution. So a unique solution exists. Well, yeah. Towards the future, at least for some small amount of time, and it also depends continuously on the boundary number. So, okay, for a future. Okay, so if you know the temperature distribution now, then you can predict it in the future, at least for some short time. Although that's not really an issue for the heat equation. And moreover, the solution you get depends continuously on these data in a suitable topology. Okay, so if you So that actually makes your theory a predictable theory. So if you always have some error in how you measure the current distribution, so you never know exactly what it is, but you do know that the solution depends continuously. So a small perturbation of the initial configuration tells you that your error is not too bad forwards in time. So that's important from a physical point of view. Okay, so that's the first important property. The next one is so-called instantaneous smoothing. So that's exactly what the name suggests. So remarkably, these initial and boundary data can be extremely general. So you don't even need them to be functions. You don't need them to be continuous. You don't even need these data to be functions. Okay, so even very rough. Example, an L2 distribution. Initial data can be evolved and become smooth for positive times. Okay? Admit solutions which are smooth, so C infinity. In the interior of omega and at positive times. Okay, so your initial thing can be extremely rough. Famously, for the heat equation, you can start off with the Dirac distribution and it immediately becomes a smooth function of positive times. Yes.
When you say you can start with conditions that aren't even functions, do you mean like distributions?
Exactly, yeah.
So like delta?
Exactly. Yeah. So I mean, the solution you get at positive times is a smooth function. It has all derivatives, everything's as nice as can be, but at the initial time, you can have something which is not even continuous and not even a function. So for example, you can have an L2, so some distribution which is in L2, and you can start off. And the famous example is that you can start with the Dirac delta distribution. Okay, so you can start off with extremely general objects, classes of generalized functions. They immediately become the most well-behaved possible functions, smooth functions. So this is a remarkable property of the heat equation. Okay, forwards in time. So you can solve this equation forwards in time. Everything gets immediately as nice as can be. We also have long time existence. So for the heat equation, in fact, it's not too hard to show that, in fact, delta can be taken to infinity. So solutions exist for all. So as long as the boundary data as long as your specified boundary data don't do something stupid, so solutions exist for all time. Okay, so this delta in the short-time existence can actually be the infinite future. And moreover, as time gets larger and larger, the heat equation evens out the temperature and forces it towards equilibrium. So, and here we get convergence. So to equilibrium. What does that mean? So probably the most robust way of saying that is that as t goes to infinity, so the function u converges to some function which satisfies the steady state equation, which is the Laplace equation. Okay? So as time goes to infinity, the solution settles down into an equilibrium state. Okay? And this convergence is actually smooth. So this happens in that smooth topology. Okay, so the function and all its derivatives settle down into this nice smooth harmonic function. Okay? In many cases, that just means that the temperature, so think about the temperature of this room, as long as there's no heat input from outside, then perfectly insulated room, no sources or sinks, then the temperature, it might be all over the place initially, but it settles down into a constant state in the far future. It evens out. So this diffusion term, Laplace operator, smooths everything out the longer the solution exists. So it has this regularizing effect on the equation. So any questions about the heat equations? Hopefully some of this sounds familiar, okay? From partial differential equations. Just think about temperature distributions. You have a hot mug of coffee, you sit it down, eventually it reaches equilibrium with the surroundings. So no matter how crazy the initial distribution of heat, it immediately sort of smooths out and starts evening out as time continues. Okay. Oh, there's another property which is very, very important. So being a pure mathematician, I forgot about this one. So this equation, the heat equation, actually models a huge amount of physical phenomena, real-world phenomena. So it's a model for a large number of phenomena, a large number of otherwise distinct appearing phenomena. So I've been banging on about heat. So it is a model, and it was originally introduced by Fourier as a model for heat conduction. But it also models things like chemical diffusion. So it's called the diffusion equation because it models all kinds of other diffusion phenomena, for example, chemical or particle diffusion. Stock prices. The Schrödinger equation in quantum mechanics is very closely related to the classical heat equation. Yes?
Is there anything that you can add on that point about Schrödinger equation?
Well, it's the heat equation with a coefficient here that's an imaginary number. That does change the behavior in many ways, but a lot of the behaviors you can still analyze it from a similar point of view. Becomes a bit more wave-like. Okay, but let me just say that even just the literal heat equation stated, a large number of seemingly disparate phenomena like stock prices or the diffusion of ideas within a society can be modeled by the same equation. Okay, and maybe another point to mention here is that, okay, you don't actually, in fact, these properties are actually stable under changing this into a more general class of parabolic equations. So you can put a far more general elliptic operator on the right-hand side of this equation, even allowing nonlinear equations and things like that, and these properties are all stable under doing that. And so, in fact, these are not really just phenomena for the heat equation, but for a whole class of so-called parabolic equations. Okay? So maybe that's a bit less familiar to some of you, but you can add gradient terms, reaction terms, things like that. You can even make it non-linearly depend on a secondary difference. Okay, and I did forget to mention at the start, but thanks for asking questions anyway. Please do interrupt me if you have any questions about it. Okay? Okay, so at some point in probably the 1960s, geometers started to realize that these properties would be extremely useful if you could say something similar within the geometric context that they were studying. So in geometry, you generally study some class of objects which you think of as your version of geometry. For example, Riemannian structures or Riemannian manifolds. So it's just some kind of topological space with a way of measuring distances and points. Maybe Yang-Mills connections in physics or harmonic maps. You don't need to know what these things are, but you have something which produces some kind of geometry. You have a whole class of objects, and the task of the geometer is to classify these objects. So what kinds of objects can arise in this way? What are the best possible versions of these objects? And if you have some kind of canonical deformation process, which sort of simplifies these objects, makes them really nice and regular, evens everything out until you get some model case, then you've got a very good chance of actually classifying this whole class of objects. So you would like in many other situations to have some similar kind of deformation process, canonical deformation process, which has some version of these properties. Okay, and there are some famous examples. So let me illustrate that with a list of with some famous examples. again, do not hesitate to interrupt me if you have any questions. If I'm not looking or paying attention, shout out, throw something at me, anything you like to get my attention. Okay, so let me, heat equations in geometry, maybe I'll call this. So let me just illustrate why it would be useful to have some version of a heat equation in different geometric contexts. So let me talk about, I think, 4 examples. So the harmonic map heat flow. Okay, so sort of generalizing harmonic functions, solutions to the Laplace equation. So a map U from one space to another, where these spaces are spaces in the Riemannian sense. So Riemannian manifolds, doesn't matter if you don't know what that means. So you've got some kind of geometric space, some other one, and a map between them. Such a map is called harmonic. If it is a critical point of the Dirichlet energy, for this, in the same way that harmonic functions are critical points of the Dirichlet energy. A critical point of okay, so this Dirichlet energy takes exactly the same form it would take for just a regular old function. You take the, is this the potential energy or the kinetic? This is the kinetic energy. Okay. So you basically look at the kinetic energy of this function u, and then look at functions which are critical points. So for example, a minimizer over all maps would have to be a critical point of this energy. Okay. And in fact, being a critical point and being suitably regular, so if and only if in a certain sense, means that U satisfies Laplace's equation, where, okay, so this all looks very much like harmonic functions, but note that basically these operators need to be defined, but they are natural generalizations of the usual gradient and the usual Laplacian, but they come from, you know, the geometric structure we have here. Okay, so these are generalizations of our harmonic functions. So in the 1960s, I think in 1964, so Eales and Sampson showed that, okay, so if you want to study harmonic functions, the first thing you want to know is whether such things exist. And Eales and Sampson showed that you can actually seek them out by using the corresponding heat equation. Okay, so such functions, such maps can be found basically by looking at the heat equation and then establishing these properties for the corresponding equation. Okay, and then looking at what happens as t goes to infinity, you end up with a harmonic by evolving non-harmonic maps by the corresponding heat flow. Okay, so if you want to try and find, you've got two Riemannian spaces, you want to, you first want to see if any harmonic maps exist. Well, one way of producing them is to take something that's not harmonic, letting it move according to the heat flow, and then show that as t goes to infinity, this thing converges to a harmonic. So that's one simple example. And this obviously is a very direct and nice, well, it is a generalization of the heat equation, because if you take n to be r and m to be Rn, this really is just the heat equation. It's just the same equation. Okay. Okay, good. So another example. I'm going to have to get down to this one. It's the so-called mean curvature flow. Okay, so one nice object which is closely related to these harmonic maps that people study are so-called minimal surfaces. So minimal surfaces. And these model a huge range of phenomena. So these are critical points of the area function. So area sigma is just, well, it's just the area. Okay, so you have some surface in space, say, or in some geometric, some Riemannian manifold. You look for critical points of the area functional, or another way to think about it is if you take some wire and you fix the boundary, and you want to look for all surfaces which minimizes the area amongst surfaces which span the given boundary. Okay, so think of soap films. These satisfy, given suitable regularity conditions, they satisfy this equation where H is the so-called mean curvature vector. You don't need to know what that means, but it's some geometric object which measures how these surfaces are curved. And this gives rise to, sorry, I won't go much into it, but it gives rise to something called the mean curvature flow, where you take your surface and you push it in the direction of its curvature. Okay, so say you've got a fixed boundary curve, you want to show that there exists some minimizer of area, or you want to find which surface minimizes the area for this given boundary curve, then you can take some non-minimizing surface and then push it in the direction of its curvature until it eventually converges to the thing with zero curvature. That thing is actually a critical point of the area, yes.
So for soap films,
yes.
What's the curvature there?
Zero.
So anywhere on a soap film, the standard curvature?
The mean curvature vanishes. So there's this particular notion of curvature. So on any given surface, for a curve, the curvature is 1 on the radius of the best fitting circle at each point. On a surface, you have a number of circles you can fit at each point. And so you take an average of the curvatures of all those best fitting circles in all directions. That's what this mean curvature is. It's the average of all of the curvatures of best fitting circles in different directions. Okay, so that's why soap films, they can look curved, but you can have some negative curvature is always balanced out by some positive curvature in a different direction. Okay? So on average, the curvature, so on average across all directions at any point, the curvature is 0. Okay, that's a very good question. There are other notions of curvature, but this one is very closely related to the area function. Okay, if things are positively curved in all directions, then they're not going to minimize area, right? You can always squash it down. So you would expect to have positive curvature to be balanced out by negative. Quick example in general relativity. So the Penrose conjecture. Okay, so I don't know if I have enough time to go through too many examples. So maybe I'll skip that and we can talk about that later if anyone's interested. So in 1982, Hamilton introduced the so-called Ricci flow. So again, you don't have to know what any of this means. This is just sort of motivation. So this is an equation. So you take a Riemannian manifold. G is a metric on a Riemannian manifold. So this is the matrix at each point, which defines your inner product on the tangent spaces. You deform that in the direction of its curvature, where here you use the notion of Ricci curvature. Okay, so you take a point on your Riemannian manifold. At each point, you deform the geometry according to how it's curved at each point. Okay, so this again forms some kind of a heat equation, and Hamilton showed that, at least in a certain special case, so metrics with Ricci positive. So if you have a sort of positive, in the sense of Ricci, curved Riemannian manifold in 3 dimensions, this does the job that the heat equation would do. So what this does, at least under these conditions, is it pushes them towards something with maximally diffuse Ricci curvature, and in fact it pushes them to something with constant curvature, okay, which is stronger than constant Ricci curvature. Three manifolds deform. So there's some rescaling, but don't worry about that. So they deform to metrics of constant curvature. So here you see what diffusion is doing for you. So if you take your geometry at each point and deform it according to how it's curved in each direction at that point, then this heat type equation, this diffusion equation, tends to average out all of the curvature until eventually at every point the curvature in all directions is the same. Okay, and there's a theorem that implies that this actually tells you something about your space. Okay, so your space cannot be a torus, for example. It actually has to be a space form. Okay, so basically your three manifold has to be topologically the sphere. I should say compact. Okay, so in any case, so your theorem tells you that, for example, the three-dimensional torus cannot admit a metric with this condition. Okay, so this was basically the starting point for. So eventually, this idea was used to classify all compact three manifolds. Okay, so this illustrates the power that this canonical deformation process has. You start off with a general three-dimensional compact space. You can deform it according to this equation. This equation smooths out all of the curvature and then decomposes it into parts that you know very well. And so then you know that the original thing you started with has to be built up from these canonical components. Okay, so I just wanted to mention this because it's a very famous application of these ideas, known as the Poincare and geometrization projections. So to date, this is the only of the Millennium Prizes that has been resolved. If you want to go out and solve any of the remaining ones, you'll get a nice painting. So that got your attention. Okay, but the point is that geometers sometime in the middle or the start of the second half of the last century, they noticed that within their respective realms of geometry, if they had some canonical process like this, which performed all of these properties, then they could resolve really important problems in their fields. And these are examples where this has been carried out. So now, okay, back to reality. That's all quite advanced. So let me just now illustrate how some of these ideas work in the simplest geometric context. Okay, so let's say we know all these nice behaviors of the heat equation, so let's apply these to some model geometric set. Okay, this is called this so-called curve shortening flow. Okay, yeah, do feel free to interrupt if you have any questions about any of that. Okay, so what is the curve shortening flow? So this is an equation which takes, well, at least in the setting of the plane, we just take some nice curve in the plane, okay? So gamma, let's just say some parameterized curve in the plane from some one-dimensional domain, and then we have some time interval. So we have some one-parameter family of curves in the plane, and we perturb these curves so that their velocity at each point, gamma is the position vector, right? So the velocity at each point we ascribe to the curvature. Okay, and we know what the curvature of a planar curve is. You just take 1 over the radius of the best fitting circle at each point and point it into the normal direction. Okay, so let's take n to be the unit normal direction. We fit the best fitting circle which curves away from the normal direction, and then we get the curvature, and then we correct the sign. Okay, so this is the so-called curve shortening flow. So this deforms planar curves in the direction of curvature. Okay, yes.
Would you be able to do a quick diagram of exactly what that best fitting curve?
Yeah, so take a let's take some nice curve here. At each point, maybe here on the curve. So we've got the normal direction. Okay, so the circle of best fit at that point has to be tangent at this point. So you take the circle, which is tangent, and well, okay, so it's the best second order Taylor approximation to your curve. So if you take a really small curve, circle, or that fits too easily on one side, you basically increase the radius of this circle to until it no longer fits locally on one side of this curve. Okay, so you make it larger and larger and larger until any larger circle goes off onto has points arbitrarily close to this point on the opposite side. Okay, but you can show that this is basically has the same second order Taylor expansion at this point. Okay, so curvature's got something to do with second derivatives of your curve. And in fact, yeah. Of course, this is locally best fitting, so I mean somewhere like this. Okay, it doesn't fit over here because it intersects, but locally near this point, it still lies to one side, or all slightly smaller ones lie to one side. So this is like a limiting case. Okay, and then you take the curvature to be 1 over r. Okay, but here this has negative curvature. Well, by our sign convention, since our normal is pointing this way, we call this negative. If the circle was on the other side, we would call it positive curvature. So this notion also picks up a sign. Okay, so that's the sort of geometric definition of curvature, but there's also an analytic definition. The curvature vector, this whole vector here, is actually the second derivative of the curve with respect to the arc length parametrization. Okay, so that's the sort of analytic definition of curvature. So it's got something to do with acceleration, second derivatives, and that's how we intuitively make sense as well. Okay. So this equation looks kind of like a heat equation. So we have d dt of gamma equals gamma ss. First time derivative is equal to second spatial derivative. This is a very heat equation looking curve. So well, not quite. There's an important difference here. So when we use the arc length parameter, so the arc length s, if you fix a point P naught, then the arc length measures the oriented distance from that point. So this is S of Q. Okay, if this is Q, then this length is the arc length relative to P naught, just fix any origin P naught. So it measures the distance. But as the curve starts evolving and moving, this distance between points changes. So S depends on T. So you have this funny heat equation where the spatial thing depends on T. If you want to use a time-independent parameter, you get something more complicated. Okay? So in terms of a fixed parameterization, which is independent of time, you get something pretty ugly. So this is what the equation looks like in terms of a fixed time independent parameter x. So this is just a dot product in plane. Okay, so here what you're doing is you're taking the second spatial derivative with respect to x, normalizing according to the speed of parameterization, and then you're projecting onto the normal vector. Okay, so you're subtracting off the tangential component. Okay, so you take the second derivative in space, normalize according to how fast you're parameterizing your curve, and then project onto the normal direction, subtract off the tangential component. So it's no longer the heat equation. It is a sort of heatish equation because we still have time derivative is related to second spatial derivatives plus lower order terms, but we also have some sort of quote unquote degeneracy, meaning that you don't pick up everything, you don't pick up the whole second spatial derivative, you're losing the tangential component. Okay, so this is, to PDE people, they would look at this and say that this looks like a degenerate nonlinear, because you've got these nonlinear terms, degenerate nonlinear system of PDE. Remember, gamma is a vector as well, so it's a system. It's got two components. Okay? So degenerate nonlinear system of parabolic PDE, which is a mouthful, and it's a mouthful because these things are hard to deal with. Nonetheless, well-posedness works. Okay, so nonetheless, so let me just say, well-posedness works. Okay, if you know anything about PDE, you would know that the difficult part of that is that this is a degenerate equation. You're losing part of the second derivatives, but the idea is that, well, you can get around that by using the geometric invariance of the equation. So we can represent this equation in many different ways. So we've already seen two different ways to represent it. We can use the arc length parameterization. We can use the standard fixed parameterization. But another really clever way to represent this equation is to take your initial curve and then represent any nearby curve as a normal perturbation. Okay? So if you have some nearby curve, you can write this point as P naught plus some normal height times the normal direction of P. Okay, so you can always, given an initial curve, you can always represent a suitably nearby curve as a so-called normal graph. Okay, and then when you can sort of work out what that means for this equation, and what you get is a non-degenerate equation for this normal graph height, which actually falls back into this setting where you can do this. Okay, so this is one way to get well-posedness. So so you can rephrase this equation in terms of the normal graph height for nearby curves, and then using that, you get an equation that already fits into this PDE theory over here, not the heat equation, but some relative of it which satisfies these properties. So you get a solution for the normal graph height, and then you can construct the curve you want just by using that function and then moving your initial curve that much in the normal direction at each point. Okay, so it's a really nice, elegant little way to get well-posedness for curve shortening flow. So what have we got? If you give me any nice enough initial curve, I can say that, well, we can start off this equation. We can start moving it in the direction of its curvature vector. Okay, you wouldn't be able to do much with this equation if you didn't know that you could start it off. Okay, so we can always get curves moving, and in fact, the same theory gives us instantaneous smoothing as well. So smoothing, so we get that as well. In fact, we can start off with, for example, Lipschitz curves. So you can start off with curves with corners, as long as they're not cusps, as long as they're Lipschitz. So if you start off with such a curve, you can start moving it according to curve shortening flow. That little corner immediately rounds off and becomes nice and smooth. Okay, and in fact, you can do better. I think the best current result is like something called rectifiable Reifenberg, whatever that means, but it's some kind of very rough notion of curves. Some fractals, for example, are rectifiable Reifenberg. So very good. We can start off our flow. We can get it going for some small amount of time, and even if our initial curve is very, very rough. So that's great. I don't want to go over time. So let me. Okay, so we also get long time existence. So let me explain what that means. So let me write it like that because it's a yes and a no. So we don't actually get existence for all times. Here's an example where that explicitly doesn't happen. If you take a circle of radius r0 and you let it move according to curve shortening flow, it just evolves, stays circular with the same origin and has radius rt equals square root r0 squared minus 2t. So this solution shrinks down to a point after time r0 squared over 2. Okay, so it only has some finite lifespan before something nasty happens. You know, the equation is no longer defined once it gets to a circle. Okay, so we don't really get long time existence. Okay, and another way to see this is to see that curvature satisfies the following. So you can show that the curvature itself satisfies a heat type equation, but it has this cubic reaction term. And so what you get is a kind of battle between these two terms, okay? So this thing is smoothing out kappa, and this thing is trying to make it blow up, blows it up, like 1 over square root 2t minus 2. This thing is exactly the solution to the equation y prime equals y cubed. And this is the general solution to the equation y prime equals y cubed. So what this term tends to do is to force the curvature to infinity in some finite time t at a certain rate. And this is exactly the rate at which the circle curvature is blowing up, right? So, yes. So you can write this as exactly where t equals 1 over 2 r0 squared. Okay, so this is actually a generic situation. At least for a closed curve, you have some finite lifespan. But on the upside, diffusion kind of loses here. We get something bad happening in finite time, but this is a worst case scenario. It turns out that nothing worse can happen. You always know that it's the curvature that goes to infinity. Another way to say that is that if you know that the curvature stays bounded, then all other derivatives of your curve stay uniformly bounded. Okay, so curvature controls everything. This is the only symptom of anything bad happening. You just have to know what happens to the curvature. Okay, so let me write that as no, yes. So okay, you always have finite time existence, but it's characterized by this curvature blow up. And so now I have just enough time to say what happens in terms of convergence. I wanted to say a little bit more, but let me just say that. Well, then we want to see what happens as the final time is approached. And what you can show is that if the initial curve, let's call it gamma t, let's call gamma t the image of this curve. Okay, if the initial curve is closed and embedded, so closed and simple, so no self-intersection, then gamma t remains closed and simple, and actually the whole curve shrinks to a point. So gamma t shrinks to a single point. as t goes to this finite lifetime till its death time. And in fact, much more is true. As it converges to that point, you rescale by this blow-up rate. Okay, so as it's shrinking to a point, you just normalize it so that the curvature stays approximately 1. And you see that diffusion actually wins out in the end. Okay? So diffusion actually, has the last laugh. It tells you that gamma t over square root 2 t minus t converges in a smooth topology to the unit circle. Okay, so as long as you zoom in order to negate this blowing up, diffusion does manage to completely uniformize the curvature. The circle has constant curvature. Okay, so I've got a couple of minutes left, I think. So that's kind of had to go a little bit quick at the end, but I just wanted to maybe put both of these on to sort of give you a visual on what this equation does. And this is a little app that Anthony Karapitis, a former PhD student at ANU, recently developed. So let's demonstrate this theorem. Don't care about the disk space. So here we have some closed simple curve. So we have some curve that closes up and it doesn't self-intersect anywhere. And then we can press play and the curve shortening flow. So you can see the regions of large curvature quickly become less sharp until they have smaller curvature. The regions of low curvature sort of move inwards and become more curved until, well, as this is trying to blow up in a point, as the curvature is sort of trying to shrink down and blow up, it becomes more and more circular. Okay, and as long as we don't do any self-intersections, this is what will happen for any initial curve, no matter how crazy you make it. Okay, and we can even have sharp corners. As long as it's nice and Lipschitz, they will smooth out, and you can see very quickly those regions of high curvature because they're moving so quickly. They due to the equation, they catch up with the less curved regions until it very quickly becomes quite circular. Now the curvature is quite small on average, and so it moves more slowly until it gets smaller and smaller. Then the motion becomes very quick. So that's an app if you want to play with yourselves at home at a.karapitis.com. You just Google curve shortening flow applet, you should be able to find it. And so it gives a nice demonstration of what's going on. Okay, I'll say one more thing, then I'm happy to take as many questions as you have. So, well, the original proof of this long time exists, so this convergence part of the proof, this is actually very, very hard to prove. Well, the original proof was very, very hard. But on my last count, since that proof appeared, another 6 proofs, very distinct proofs, logically distinct proofs, have appeared, including 2 which were due to Ben Andrews, who's upstairs there somewhere. Extremely elegant, simple proofs, the proof of which I could give you in one lecture, the whole proof of that theorem. So if you want to learn about that, I think Ben is running a topics in geometric analysis class as well. So I don't know if he's going to talk about curve shortening flow, but he has the sort of slick proof of this theorem. So at least 3 of those proofs are somehow related to the MSI. Okay, so I'll stop there. Sorry for going on very quickly and a little bit long. Happy to take questions from anyone if you have any.
What are some other applications of all sorts of curve shortening flow?
That's a very good question. So that's, I promise I didn't plant him in the audience. That's something I missed out and didn't get to that I wanted to talk about. So perhaps you meant mathematical applications, but I did want to outline some sort of non-mathematical applications. And in fact, the earliest paper that I'm aware of on curve shortening flow is due to John von Neumann in 1952. In a journal called, it's called, I can't remember the journal, but it was a journal of the American Society for Testing Materials. So in fact, this wasn't even a mathematical context. He was proposing it as a model for the evolution of grain boundaries in annealing metals. So when you heat metals up, this sort of atomic structure has some crystallizing property, and there's sort of a boundary between the region that is non-crystallized and crystallized. And I think this is This is what it is, and this boundary moves according to the curve shortening flow, at least according to John von Neumann. There have been it's since been proposed as a model for wearing processes, liquid interfaces. So anywhere where you have dynamics involving surface tension. So this curvature kappa, it is the mean curvature for a curve. So it's related to those minimal surfaces, those soap films, but in a one-dimensional setting. So anywhere where you have surface tension, and also image processing. It was really famously used in image processing. One of the most highly cited papers in mathematics by Osher and Sethian is on using curve shortening flow in image processing. It's even appeared in the context of quantum field theory, and if you know what it means, because I don't really, cellular automata, which is a new field. It's appeared there. I won't say it's a fundamental aspect of those fields. So that's just a bunch of wider applications of curve shortening flow. Is that what you had in mind, or were you thinking mathematical?
No, I was thinking exactly that.
Okay, yeah. There are also mathematical applications, but I've spoken too much today, so happy to take any more questions. Yes?
What are the next things of research? Like you said, there were multiple proofs for this conversion.
Oh, great.
Build on this.
That's a great question. So this is sort of the simplest setting for curve shortening flow. So there's a higher dimensional generalization where instead of curves in the plane, you could look at replacing 1 by 2 and 2 by 3, look at surfaces in space. And in fact, there's a number of things you can now replace this curvature by. You could use the mean curvature vector that we saw before. That's one option. So in higher dimensions, the mean curvature flow is a huge area of study, and there's a lot of open questions, even for surfaces in R3. So for example, this convergence result, there's no obstruction to this happening topologically. So you sort of already know from the Jordan curve theorem that such a curve is a circle topologically. But for surfaces in R3, you can't hope for such a nice result because you can have things with handles or multiple handles. The topology is much more complicated. You could potentially hope to converge to one of those standard surfaces, but it's awesome. Okay, so not only is there no obstruction here, that doesn't imply that this flow will actually do this nice job for you. If you go one dimension higher, it doesn't. So even though you sort of already know what the obstructions are, it still runs into a lot of problems. That's one generalization. You can add different boundary conditions instead of doing closed curves. You can look at the Neumann condition. There's still a lot of interesting questions which remain open just for curve shortening flow, even with Neumann boundary condition. You can look at replacing kappa by something anisotropic, so you can add basically a gradient term. So you can add something that weights this velocity different in different directions. So if your normal direction happens to be that way, you maybe multiply by 2, whereas if you're going that way, you multiply by 1, which sort of tends to move so if you add sort of anisotropies, which actually come up in applications, crystallography and stuff like that. So even for curves in the plane, there's a number of interesting research directions there. I could go on and on, but that's just a little sample. Yeah. Any other questions?
As an off-topic question, but I'm curious that if a closed trap surface is satisfied with a curvature flow.
Closed trap surface. Yes, good question. So let's see. So I did want to mention the Penrose inequality. So in general relativity, you can look at so-called time-symmetric initial data sets, which I think you'll know what I mean by time-symmetric. So that's a special kind of three-dimensional space-like slice in general relativity. And so you can look at two-dimensional surfaces in that three-dimensional space-like slice. And you can evolve these by, so Gerock noticed that if you evolve these by something called the inverse mean curvature flow, where instead of kappa here, you put kappa to the -1, but then you go up to mean curvature instead of one dimension. Then something called the Hawking mass is monotone under this flow. And so his idea was that, well, this should lead to a proof of the famous Penrose inequality, and that works. But your question was about mean curvature flow of space-like surfaces, is that right? So there's a number of interesting questions in that setting where you might hope to use mean curvature flow. It's being used well, in a number of ways. One interesting application of mean curvature flow in initial data sets in general relativity is to give a canonical definition for center of mass. So in physics, in classical physics, you can sort of integrate over your mass distribution times the position, I think, gives you a well-defined notion of center of mass. In general relativity, these concepts are much harder to define. I won't be able to explain how today, but you can actually use this flow method to give a canonical definition for center of mass in general relativity. You can certainly use the flow in that setting. They have mean curvature and whatnot, but there are also nice applications. Yes?
On that mean, is the curve, do you know that the mean point, like if you did a kind of center of mass for a curve, if you're doing this curve shortening, do you know that your center of mass is staying at the same point? Or is it possible that the curve can like shift about?
That's a really good question. I don't know if I know the answer. I think the center of mass, let's see, it's certainly a useful quantity to consider. My guess, I might be wrong, but from memory, I think that this point might be the center of mass. I might be wrong, but that's a really good question. Yeah, so you can define the center of mass for the curve by integrating over. I can't remember exactly what you integrate over, but I think the final point that is preserved in the final point is the center of mass. Check that though, I might be wrong. Okay, I probably better stop there. Is that?
Yeah, that's good. Just so like people can like if they need to go to classes.
Yeah.
We got some sushi, so you guys want to eat and still mingle around and chat longer.
Yeah, awesome.
That's cool. I'll double check if no one's booked this room 2.5. Otherwise, thank you very much.
Yeah, no worries. Thank you. Ben's class, topics in geometric analysis. If you really want to learn more about this stuff. If anyone wants to play with this, feel free.
If you intersect yourself, does it throw a problem?
That's a great question. So here it gives numerical problems. But you can see that this won't just be a numerical problem. Something really mathematically has to go bad. You could also, there are many ways to self-intersect. So you can, let's see. So I could have a curve with 0 turning number like this. Or I could have turning number 2 like this. So these curves obviously have to have something bad happening because topologically they're not really this kind of a circle.
So would self-intersections there relate to non-spherical topologies in higher dimensions?
In higher dimensions, yeah,
where
things
like,
are much
you've got
different.
this extra singularity.
Yeah, so you have that extra singularity here in curve shortening flow. So that theorem only works if you're embedded. So and definitely something goes wrong here. So I mean, it's not too hard to show that such a curve necessarily has to have a cusp-like singularity that you just saw. You can model that canonically. It sort of has a canonical shape as well, but in higher dimensions, you can't really have things like this because surfaces are